I'm Ichiro, and I'm joined by Whitney, Najib, Aaron, Akash, Joni, Brian, and Benjamin. Our project was a capstone for the Alaska Center for Energy and Power, ACEP, and our industry mentor is Daha Nur. Our faculty mentor is Rajesh Subramanian. Our product is making an LLM for energy research papers.
So why a large language model? Well, you see, for any researcher, the most time-consuming step of research is finding relevant research documents. So imagine, rather than looking through a bunch of research documents, trying to find relevant ones to your research, you could just query some LLM chatbot that already had all that information memorized and would then tell you which documents are most relevant to your research. In a way, it's bringing them to the surface so you don't have to dive so deep. The idea here is not just to make this chatbot, but also to make it modular so that everyone can tailor it and shift out different parts as they please, while also making it open source, as you'll see on the last slide where we have our GitHub. The goal is to make it something that looks like Perplexity AI and functions kind of similar. Perplexity AI allows you to enter a query. It'll then search the internet for relevant sources to this query and return them to you, as well as a summary of those sources. Our goal is to have our chatbot basically have some database stored with the relevant documents already in it for any type of research, primarily energy-related documents. So then you could then put in your information in there, and the chatbot would query your information, making it tailored to you.
So to give you guys a quick overall project concept, we start off with the documents in PDF form. Those are fed into our OCR, our optical character recognition model. That just pulls out all the textual information from the PDFs and allows it to be understood by the machine. Those textual blocks are then fed into JSON, which are file formats that are just text-rich. Those are then created into embeddings, which are fed into the vector database. That allows it to be referenced by the LLM for later use. These last three blocks here, the LLM, Flask, and the website, are kind of where the magic happens. Whenever you send a query back through the website, the backend replying part for that is Flask. That queries the LLM, which then references the vector database to find the most relevant information to create the response, which is then fed back through Flask to the website for you to be able to see. And to start our implementation right here, we start off with the documents in PDF form, of course, and the OCR model we're using for here is Tesseract. And passing down to Najib.
Thank you, Ichiro. So yeah, once our optical character recognition model, Tesseract, pulls out that text from those PDFs, we want to pass that text into a chunker. So basically, we don't want all the text from every single PDF to be within each document. We want to split each PDF into mini documents with chunks of text instead, say a couple sentences. These chunks are then converted into JSON format, and appended onto them is some metadata relevant to that document. So as you can see on the right, we have, for example, our document ID, the title, the author, and then you can see that text field that basically is that text that's being embedded later on into the vector database, as I'll talk about in a second. And at the bottom, you can see what that vector actually looks like. So after the embedding, you'll see that that chunk basically gets converted into like a list of numbers, a vector, and stored in the vector database to allow for easy querying later on. So that JSON file is then sent to the vector database, and the LLM then can query that vector database and figure out what relevant documents it needs to reference, summarize them, and then return them back to the user. How does it return it back to the user? Well, Aaron will get into this a bit more into a couple slides later, but we're using Flask, which basically is connecting our backend to our front end. And so we can pass in those results from the LLM out to the front end, where the front end can make it look nice and pretty in a chat format.
Yeah, now I'm going to talk about query flow. First, a user sends a query, which we convert to an embeddings, which is a numerical representation of the text data, like Najib said before. Then, we pass this query's embeddings to our vector database, which allow us to find the most similar and relevant chunks of information that's already stored in the database. Once we retrieve these similar chunks, we prepare a hidden prompt that includes both the retrieved information and the original user query, providing essential context for our large language models. Then the large language model will process and combine the input to generate a response based on the provided context. Finally, we take this response and send it back to the user. This entire process happens seamlessly, ensuring the user receives an accurate and contextually relevant answers.
So a lot of our design choices were motivated by trying to achieve maximum modularity. So since we were trying to achieve maximum modularity, we ended up doing our data pipeline entirely in Python. So what we needed were tools that were friendly with Python, so Python APIs. Two Python APIs that we ended up using are Together.ai and MongoDB. Together AI is a very popular API that provides access to hundreds of open source LLMs and embedding models. We are using their Llama 3 and M2 Bird models for their LLM and embedding models, respectively. MongoDB is a very robust database. It provides us with the Atlas search, which is an excellent vector search that we use. On top of that, it's got a very strong community and straightforward integration with Python. Flask is a Python framework that allows communication with websites and other apps through HTTP. So we're able to use Python to write a Flask app that contains all of our query code integrated with Together.ai and MongoDB to seamlessly return responses to the user. Now all that's left is a place to host the Flask app, which is where Google Cloud Run comes in. It's hosted serverlessly, and it dynamically allocates resources depending on how many people are using the website, and it can listen and receive requests from the front end.
Right. So ACEP has a huge database of files, which can be a real pain to have to search through. So as a solution to this, we have designed and implemented a chatbot that will answer questions and direct users to the proper files that the user is looking for. Our chatbot is able to cater to our users' personal needs using personalities, which Whitney will go into later. And we are able to answer questions and connect them to the LLM so that the user does not have to search through all of these files so that they can find answers to their questions. And now I will pass it on to Brian.
Thank you. So the overall combinations in our front end, including Axios, React, Cloudflare page, and then the website itself, creates an efficient and user-friendly system. For the connections with our backend, we use Axios to send HTTP requests from the browser, and the Axios can be easily built in the React applications for the connection. And React is the JavaScript library for building user interfaces. Where it's particularly important for the single-page applications where you need a fast, interactive user experience. Its key features include the virtual DOM for efficient re-rendering and the component-based architecture for reusability and the better management of our code base. With these features fit our needs for the seamless integrations and the development. So that's the part of implementation.
So now I'm going to provide a brief demo of our chatbot in action. So we decided to host our webpage on Cloudflare Pages because it provides an affordable and easy way to configure custom subdomains. It also provides built-in analytics regarding user traffic and the performance of the website itself. And it also has the capabilities to automatically connect with the GitHub repo where your code is stored, and every time changes are pushed, it will automatically redeploy. And our GitHub repo is linked right at the top of our webpage. In addition to, we've provided an about and documentation page using the hamburger menu on the left side. So if a developer wanted to redeploy this on their own to fit their use cases, they would be able to learn more about how we did that here. So when a user accesses our webpage, we have a brief kind of summary of why our chatbot was created and how it can help, in addition to an introduction for how the chatbot responses can be customized based on user needs. So on the right side, the user has the ability to choose a personality that will curate the responses based on specifically what they're looking for. So if we want some follow-up questions, and we want the LLM to dive more into what we're looking for, we can pick the investigative personality. And let's say we ask it to tell me about the energy situation in Alaska. Here we go. So the user can send their query, and that's going to send back to the backend. And as they discussed earlier, the vector database is going to find the 5 sources most relevant and that's what's going to be used to provide this brief summary of a response. In addition, because it was investigative, we can see the LLM is asking follow-up questions so that it can find more specifically what the user is looking for. The response will also mention or reference the sources from where they found their answer.
You can also find these sources in a tabular format. So that's what we're going to be doing right now. In a tabular form, present the best documents you can find relating to energy consumption and elaborate on your reasoning. We're also going to change the personality to a different one so you can see how the different personalities tailor your response. You can see here that in the tabular format is given document title, as well as author year and the relevant score to our to the user's query, which helps research a lot. And again, you can use the view PDF to see where the large language model was able to get its information from. Here we have another query about solenoids. In this response, you can see that there wasn't any direct mentions in the documents, but the large language model will give other information based on your query and still give sources that may relate to a researcher's query. And yeah, that is our demo.